Working with the large-scale geospatial data. Welcome to a new lecture of Advanced Geospatial AI, Deep Learning for Satellite Imagery Analysis. I am Dr. Asad Rasul, and today we are diving into handling large-scale geospatial data for deep learning. We will now tile a large Sentinel-2 image into 16 patches, normalize, and augment them for CNN training. By then, you will run this workflow in Colab, producing tiles ready for models like ResNet 18. Challenges of large-scale geospatial data. Satellite imagery like Sentinel-2 stem-meter resolution sense can span thousands of pixels, often gigabytes in size. This creates challenges for deep learning. First, memory constraints. Full images exceeds GPU memory limits even in collapse-free TI. Second, processing time. Training CNNs on entire sense is slow without optimization. Third, data variety. Large datasets need efficient pipelines to capture diverse land cover types, like forests and urban areas, for accurate classification. To tackle this, we will use tiling to split images into megabytes, 256 by 256 patches, batch processing for efficient training, and augmentation to increase that data diversity. These challenges are key for applications like crop monitoring, targeting accuracies above 95%. Techniques for handling large-scale data. Here are three essential techniques for large-scale geospatial data. First, tiling. Split large images into smaller patches to fit GPU memory and enable batch training. Second, batch processing. Pre-processing and load tiles in batches to optimize GPU usage and speed up training. Third, data pipelines. Use GE to stream Sentinel-2 data and pre-process styles on the fly, minimizing storage needs. In today's demo, you will tile a 10 by 10 kilometer Sentinel image into 16 patches, normalize all tiles, and apply a simple augmentation. We will use GE to access Sentinel-2 imagery, NumPy for tiling, and albumentations for augmentation, all in Google Colab. The demo will load a large Sentinel-2 image, tile it into 16 patches, normalize them to 1 to 0, and apply a horizontal flip augmentation, preparing all tiles for CNN training in a real-world geospatial workflow. Coding demo. Let's jump into the demo in Google Colab to tile a Sentinel-2 image and pre-process all 16 tiles. Open the Jupyter Notebook from the course resources and follow along. Install required libraries. Let's kick off the lecture by setting up our environment. In Colab, we are using OpenCV for potential image processing, NumPy for array operations, albumentations for augmentation, and GEMAP for Google Earth Engine data. These libraries, typically pre-installed, prepare us to handle large-scale Sentinel-2 imagery for deep learning. Then import libraries. Here we import our tools, CV2 for image handling, NumPy for arrays, albumentations for data augmentation, and EE and GE map for Sentinel-2 access. We also bring in random and torch for reproducibility to process all tiles efficiently. Then we set a random set of 42 for Python, NumPy, and PyTorch to ensure consistent tiling and augmentation results. This reproducibility is critical for large-scale experiments, so our CNN training remains reliable across runs. Authenticate and initialize GE. We connect to GE with the same project, my project test 399218, that try accept block checks, authentication, prompting logging in Colab if needed. This ensures we can access real Sentinel-2 data for our larger 10 by 10 kilometer region. Then define a region of interest. We define a 10 by 10 kilometer region in Feijó, Brazil, at Sentinel-2's 10-meter resolution. This gives us a roughly 1000 by 1000 pixel image, ideal for demonstrating tiling for large-scale deep learning tasks. Next step, retrieve real Sentinel-2 Level-2A data. Then check if image exists. We retrieve a cloud-free Sentinel-2 Level-2A image from June 2023, filtering for less than 10% cloud cover and sorting by time for consistency. We check if an image was found to ensure our pipeline is robust. Then log image ID for reproducibility. We print the image ID to confirm we are using the same Sentinel-2 image each time. This ID shows here ensures reproducibility for our large-scale tiling, critical for consistent results across runs. Select bands. We select red, green, blue, and near infrared bands B4, B3, B2, and B8. These bands capture visible and vegetation signals, perfect for land cover classification. And we will preprocess all 16 tiles for CNN training. Next step, exporting to NumPy array and cache. Then validate input array shape. We convert the image to a NumPy array and cache it to avoid repeated GE calls. The output shows a 999 by 996 image with 4 channels, slightly off from 1000 by 1000 due to GE's projection. We transpose to channels first format, preparing for tiling all patches. Then pad array to create a 4 by 4 grid of 256 by 256 tiles. Now we tile the padded array into 16 patches, each 256 by 256 pixels with 4 channels. The output confirms we have 16 tiles, each perfectly sized for CNN input, like ResNet 18. We added per tile padding for edge faces, ensuring all tiles are uniform. The next step, normalize all tiles to 0 to 1. We normalize all 16 tiles to a 0 to 1 range by dividing by 10,000. This stabilizes training for our CNN, ensuring consistent scaling across large data sets. The next step, applying minimal augmentation to all tiles. We apply a simple horizontal flip to 50% probability to all tiles. adding diversity for training without changing pixel values. We use a unique seed per tile for reproducibility, transport for augmentations, and clip values to stay between 0 to 1. Print sample values for first and last tiles. Finally, we print sample pixel values for the first and last tiles. The first tile is high near value 0.34 shows vegetation in Feijó. The last tile at the image edge has lower values but still reflects real data. These 16 tiles are now ready for batching and training. Let's run the code. Select T4 GPU, then run. Executing. Choose Allow. Select on the email. Continue and continue. The output, image ID, input array shape before transpose, 999 and 996 for channels, input array shape after transpose, for channel 999 and 996. Add the image shape for channels 1024 and 1024. Original image shape and number of tiles 16 tile shape for channel 256 by 256. The value of normalized tile sample, first tile, augmented tile sample, first tile, then normalized tile sample for the last tile, and augmented tile sample for last tile. Let's rerun it to avoid these zeros. Now, last tile augmented tile sample 0.017, first band 0.029, second band and 0.018, and near band 0.26. To sum up, today we mastered tiling and preprocessing large-scale Sentinel-2 imagery for deep learning. You process 60 tiles in Colab, ready for a CNN like ResNet 18. Action items: run the notebook to tile and preprocess the Sentinel-2 image. Complete the assignment. Tile a new Sentinel-2 image and record normalized augment values for two tiles in Q&A session of Udemy course, and take the quiz to test your understanding. Let's keep advancing your geospatial AI skills.